Okay, good afternoon, everyone. Questions about the homework? Please, we start with that as usual. 5.2, number 11 and 13. Okay, we look at those. Okay, I look at them. All right, and in this question is, now 11, 13 are the same. So I usually pick one of them. I will not do both. So we have the following matrix. 4, 5, minus 2. And 0, 3, 0. And 0, 2, 2. Okay. And if my memory is right, I asked you to do the following. I asked you to find the eigenvalues, and I asked you to find the basis for the eigenspace that correspond to each eigenvalue. So first, you're going to find the eigenvalues, and you will do more problem today along those lines. Okay. So to find those, we have to compute. So this is my matrix A. We're going to take the determinant. We set the determinant of A minus lambda equal to 0, and we solve for lambda. Okay, so let us see what's the determinant of A minus lambda I. If I remember, we took a lambda from every term along the diagonal. That's 0. 3 minus lambda is 0. 0, 2, 2 minus lambda. So when I take A minus lambda I, it's really equivalent to take lambda from the term along the diagonal. All right, now we have to compute the determinant. And of course, when we study the determinant, we immediately, you have to study a cofactor expansion. So when I find the determinant, and I find what's the easiest way to do it. In this problem, definitely cofactor down the second column is the easiest way. Okay, and that's exactly what we are going to do, because I have lots of zeros. Or you can do the first row. I don't know why I picked that. Or you can do the first row, actually. So why I'm doing this, sorry. It doesn't really matter. So we're going to do cofactor across the first row. I will get 4 minus lambda, 0, 0 times this. Okay, so which is actually simple. So it's 4 minus lambda times 3 minus lambda times 2 minus lambda. This is equal to 0. Means we have 3 eigenvalues. Lambda equal 4 from this. Lambda equal 3. Lambda equal to 2. And all of them have algebraic multiplicity 1. Now the question is find a basis for the eigenspace that correspond to each one. Again, I will pick one eigenvalue. I will not do all of them. Okay, so because I will do more problem along those lines today. So let us find a basis for, let's see the notation, E4. It means the eigenspace that correspond to lambda equal to 4. Remember, the eigenspace is all the eigenvectors with the 0 vector thrown into the midst. All right, to do that, we need to solve A minus 4i. We have to solve this system, x equal to 0. Because as I said several times, this is really equivalent to solve ax equal 4x. And this is really what the eigenvectors are. Those x's such that AX stretch by a factor of 4. So instead of solving this, we solve the simpler homogeneous system. Okay, so we're going to do that. A minus 4I, 0. Okay, and this is equal to. So I have to take a 4 from this. So that's going to give me 4 minus 4. That's a 0, 0, 0. And then say 5. And then 3 minus 4. And say 2. And that's a minus 2, 0, and a minus 2. And it's just a matter of solving the system. We have to go to the echelon form. So I'm going to kind of switch things around. All the rows of zeros have to go to the bottom because no rows of zeros. So I will have minus 2, 0, minus 2. That's the row of 0 has to go here. And then it's a 5, minus 1, and a 2. I want to go to the echelon form, so I have to get rid of this 5. But, you know, we're smart enough. Having minus 2, minus 2, I would rather first divide by negative 2. So to make this is a 1, make the math much easier for me. And now this is a 5, minus 1, 2, 0, 0. So I did that. So I divided the first row by minus a half to make this math simpler because I'm doing it by hand. And now we have to solve the system. So we do that. Keep it in front of me. So this is going to give me the following. 1, 0, 1, 0. Minus 5 plus 5, it's a 0. And minus 5, that's a minus 1. Minus 5 plus 2, that's a minus 3, 0, 0, 0. Okay. And now we just solve. Leading, leading. X3 is free. So this is going to give me X3 is free. The second row read minus X2 minus 3X3 equal to 0. It means X2 equal minus 3X3. The first row read X1 plus X3 equal to 0. X1 is minus X3. Now, as usual, I'm going to put, I call T my free variable, and I rewrite the solution in vector form. So it's going to give me negative T, negative 3T, and T. I factor out my T, give me minus 1, minus 3, and 1. Okay, so what does this mean? It means that the eigenspace E4 are all the eigenvectors, but every eigenvector is a scalar multiple of that. So E4 is nothing more than the span of this vector. Because E4 is all the eigenvectors that correspond to lambda equal to 4. And this shows me that all the eigenvectors that correspond to lambda equal to 4 are of the form a scalar times that. It means E4 is the span of minus 1, minus 3. So the basis for E4 is actually this vector. Okay. Now for the other eigenvalue, we repeat the same thing over and over and over, which definitely I will not be doing right now. And number 13 is verbatim the same. There is nothing really different about it, right? Okay, now we're going to move to section 5.3, the idea of diagonalization. So section 5.3, diagonalization. Diagonalization. Okay. First, a definition. Definition. Okay. Suppose A, I read it, so you guys can write it here, which is easy. Okay. Suppose A is a n by n matrix. So A is a n by n matrix. Then we say that A is diagonalizable. I know it's weird for you right now. If we can find a diagonal matrix D and an invertible matrix P such that A could be factored out as a P times the diagonal times P inverse. So a matrix is diagonalizable. So A, suppose A n by n. A diagonalizable if I can factor out the A like this, a certain matrix P, a diagonal matrix P, and the inverse, where D is diagonal. Diagonal means that it has term along the diagonal and everything else is zero. That's a diagonal matrix, where T diagonal and P invertible. And both are n by n. Okay. Now, before we get into this, how to decompose, let us see a very small application, very kind of interesting application to this idea. So some kind of an application. Actually, this chapter is an application to eigenvectors, eigenvalue. Okay, application. First, suppose I have a diagonal matrix D. Suppose D is diagonal. And let us say, I'm going to take a simple example. Suppose D is this matrix. I'm going to put 2, 0, 0, 4. So just a 2 by 2 diagonal matrix. And I'm going to start taking powers of D. What do I mean? Suppose I take D and multiply it by itself. What happened to the matrix? If it's a matrix diagonal, multiplied by itself. So D squared, it means D times D. I multiply it. Okay, we're going to multiply row, column, 2 times 2, 0, 0, 0. We get 4 squared. So it's a diagonal matrix. When I multiply it by itself, it's like really boiling down to squaring those and squaring the second entry. Suppose I will take D to the power 3. What's D to the power 3? It means D times D times D. Same thing like what D squared is. Let's see what do we get. D times D, I've just evaluated it. 0, 0, 4 square. I multiply, so this is D squared. I'm going to multiply it by D, which is 2, 0, 0, 4. And hopefully you guys see the pattern. 2 squared times 2 to the power 3. 0, 0, 0, 4 to the power 3. Okay, so if I have a diagonal matrix, and that's crucial here. If I take it and multiply it by itself 3 times, it's really equivalent to take the terms along the diagonal, and this is D to the power 3. I raise the term along the diagonal to the power 3. So in general, we have the following simple fact. So what we can show that if I take D, as long as D diagonal, and I raise it to the power k, I will get 2 to the k, 0, 0, 4 to the k. So multiplying a diagonal matrix by itself is actually kind of simple. Now, let us say we have the following. Now, suppose I have a matrix A, and I can factor it out, break it into easier matrix. Suppose I can factor it out into a matrix P, a diagonal matrix, and P inverse. Okay, so in other words, I can diagonalize it. So suppose A could be written like that. Let us compute A squared. What is A squared? It's A times A. Let's see, is equal to what? It's P times D times P inverse times P times P times P inverse. It's A times A. So this is equal to what? P inverse times P, that's the identity. So it's going to give me D times the identity times T times P inverse. So a little bit of math, it's P times D squared times P inverse. So A squared is equal to that. So if I multiply A by itself, if I can factor A like that, is P times D squared times P inverse. Now, let's see. If I compute A to the power 3, which is A squared times A, we're going to have the same ideas. Times P inverse, that's the A squared, times P times A times P inverse. Again, I can combine those two, which give me the identity. So this will become P D to the power 3 times D inverse. And the pattern continues. So it means that in general, if I can decompose the matrix, if I take A to any power, as long as K is an integer, like A to Q, A to power 3, A to power 100, then A to the power K is just P times dk times P inverse. So if I can decompose a matrix, then the power of the matrix are very easily computed. So we can very easily compute the power. So let us say I have the following matrix. Suppose that somehow I have a matrix A, and this is my matrix. Okay. Sorry. Okay. Suppose I have a matrix A, and this matrix, I can write it like this. And very soon we're going to see how we do that. 1, 2, this way, and 2, 0, 0, 4. And this is my P. That's my diagonal. And this is my P inverse. Now we can compute P inverse. It's easy for us. And let us say this is equal to that. Okay, that's my A. So I can write it as a product of 3 matrices. And I tell you, compute A to the power 10. Okay, now multiplying A by itself 10 times is nothing more than a nightmare in the making. But if I can write it like this, what this tells me that A to any power, if I can decompose it this way, is going to be equal to P times D to the power N times the P inverse. Now, D is easy to compute. D is diagonal. So D is diagonal. So D to the power N, we just trace the element along the diagonal to the power 10 times P inverse. That's A to the 10. So instead of having to multiply A by itself 10 times, if my matrix happen to be diagonalizable, it means if I can factor it out, if it can be factored out like this, and then compute A to any power, it's becoming really a much simpler problem. It's really boiling down to multiply 3 matrices by each other instead of multiplying a matrix 10 times by each other. Okay, so that's one small application to the idea of factoring. So we can basically work with this matrix better than before because diagonal are easy and those are invertible matrices. So this allows us to work with the matrix easier than it is an arbitrary matrix. So the question here in today's section is the following. Is every matrix diagonalizable? It means, can I factor out every matrix this way? Second, what's the P and what's the D in this matrix? So if I can factor it out, what is the D and what is the P? So our question is the following. So the big questions of today that we're going to solve is the following. So the questions are, okay, which matrices are diagonalizable? Is which one I can factor out. So, question number 1. And question number 2, how to diagonalize. It means what is P and what's D. So if my matrix A is P, D, P inverse, my question, which one I can write them this way? And what's going to be this? And what's going to be that? So that's really the heart of this section. All right, so first I will motivate where everything comes from. It's going to be a little bit theoretical in nature. Once I do that, then we do a lot of diagonalization. But before I do that, let me motivate where the whole concept is going to come from. So let us say, suppose A is 2 by 2, because simple matrix, A 2 by 2. And let us say I can factor it out. Suppose we can do that. Suppose we can do that. The question is, what's the P? What's the connection to the A? All right. Okay, if P is 2 by 2, so P is going to be a matrix. And I'm going to call its entry V1, V2, because it's a 2 by 2. So I call this V1 and this V2. This diagonal, I'm going to call its entries lambda 1, lambda 2. Why not? And this is 0. And the question is, what are those? What are those? All right. So suppose we can do that. A could be B. I'm going to write multiply by P. Write multiply by P. If I write multiply by P, I will get A times P equal P times D. 2 more steps and we understand the whole picture. All right. But what is P? Suppose I said P is V1, V2. It means that this is A V1, V2 equal P times D. So P is, P is P times D, which is lambda 1, 0, 0, lambda 2. And now I'm going to use a fact that we've talked about, multiplication. Okay, let us see at the beginning, when we talked about multiplication, I said that there is a fact about multiplication that we use more theoretical than in computation. If I multiply A by V1, this is the same thing as, I can kind of distribute the A. So this is the same thing as AV1, AV2. That's the property of multiplication. And I'm going to do that here. This is the same thing as P times L1, 0, and I'm going to distribute the P. All right. So just give me that AV1, AV2 equal. Now I'm going to analyze that. Again, what's P times L1, 0? What's P times L1, 0? Let's compute this. P is V1, V2. If I multiply it by lambda 1, 0, and we use a definition of matrix times a vector is a linear combination of the columns of A, this is lambda 1, V1. So if I compute that, this piece here will be lambda 1, V1. And this piece here will be lambda 2, V2. So I know it's a little bit hard for you, but that's so we can understand the concept. So if I have a matrix, if I can factor it out this way, okay? And if I call V1, V2 the columns of P, lambda 1, lambda 2 the diagonal, then if this occurs, then this matrix has to be equal to that. What does this mean? It means AV1 should be equal to lambda 1, V1. And AV2 should be equal to lambda 2, V2. But what does this mean? What does this mean? So if my matrix P is V1, V2, and D is lambda 1, lambda 2. If I can factor out this matrix, then AV1 equal lambda 1, V1, AV2 should be equal to lambda 2, V2. It means V1 is what? And V2 is what? Who can answer this question? So if this is possible, if I can factor, and if I let P to be, the column of P to be V1, V2, and I call the columns of A lambda 1, the terms around lambda 1, lambda 2. So if I can factor, then A V1 should be equal lambda 1, V1. It means what is V1 for the matrix A? What does it represent? What does it represent? If A V1 equal lambda 1, V1, it means V1 is what for the matrix A? No, V1 is what? Is an eigenvector. So V1 is an eigenvector for A with eigenvalue lambda 1. Eigenvalue lambda 1. So if I can do this decomposition, V1 is actually going to be an eigenvector for A1 with eigenvalue lambda 1. So eigenvectors come out of nowhere. They're extremely useful. They show up with us almost any time without really knowing they will show up. V2 is going to be the eigenvector of A2, sorry, of A with eigenvalue lambda 2. Lambda 2. Okay, so if this factorization is possible, the P, the columns of P will be the eigenvectors of A. And the term along the diagonal for D are going to be the eigenvectors and the eigenvalue. Sorry, the eigenvalues that correspond to V1 and V2. One more thing. For P to be invertible, for B to be invertible, because we want P times D times P inverse. For V to be invertible, the columns of P has to be linearly independent. It means for P to be invertible, the matrix A needs to have linearly independent eigenvectors. Otherwise, the P will not be invertible. So I'll sum up this in, we're going to sum the whole idea in a theorem. So if I can factor the matrix this way, this matrix P will have 4 column eigenvectors. For it to be invertible, for this to occur, those has to be linearly independent. Otherwise, we cannot invert it. And the terms along the diagonal of D are going to be the eigenvalues that correspond to V1 and V2. And that will be the content of our major theorem today before we apply. So the theorem, the diagonalization theorem. It says the following. Suppose A is a n by n matrix. Then the matrix A is diagonalizable. It means I can factor it this way. I can factor it if A has n linearly independent eigenvectors. In the previous problem, because I had 2 by 2, and if I can factor it, because it was 2 by 2, the columns of P has to be the eigenvectors. But for this to be invertible, if those are not linearly independent, then the P inverse doesn't exist and everything doesn't really make sense. So the main criteria for diagonalization, a matrix diagonalizable if and only if it has n linearly independent eigenvectors. Now, if V1 through Vn are those eigenvectors, so let us say it had those. So if V1 and Vn are those eigenvectors with corresponding eigenvalues, lambda 1 through lambda n, repeated according to their multiplicity. It means, let us say lambda 1 has algebraic multiplicity 2, I'm going to repeat it 2 times. This will be explained in the examples. So, and repeat according to their multiplicity, then A could be written as P times D times P inverse, where P will have for columns those n linearly independent eigenvectors, and D will have along its diagonal the eigenvalues that correspond to those eigenvectors. So if this is V1, this would be the eigenvalue that corresponds to V1. The order is going to be important. If this is V2, this will be the eigenvalue that correspond to V2. So characterization, diagonalization, we can factor out the matrix or we can diagonalize it if it has n linearly independent eigenvectors. That's the criteria. If it has those, the way we diagonalize it is that P will have for columns the eigenvectors, D will have along the diagonal the eigenvalue. Both of them will have to be n by n matrices. So here, so the theorem states immediately, I repeat the idea that a matrix A is diagonalizable if it has n linearly independent eigenvectors. It means it has to have enough eigenvectors to form a basis for Rn, because we know that n linearly independent vectors form a basis. So for matrix to be diagonalizable, we need enough eigenvectors to form a basis for Rn. Now we're going to basically take problems and we are going to diagonalize them if possible to make the idea a little bit clear. So I start with the following problem and then we'll proceed. So I write it down so I don't read it. So we're going to take the following example. Let A be the following matrix: 1, 2, 5, 4. And the question is, diagonalize A if possible. The matrix A if possible. It's possible to diagonalize if you can give me 2 linearly independent eigenvectors. So the only way to do that is we have to go after the eigenvectors. So we have to find the eigenvalues, then we find eigenvectors, and then we see if we have enough linearly independent one. So that's how we're going to proceed. So step number 1, we're going to find the eigenvalues. So problem that it doesn't seem related to the eigenvalue, but it's absolutely related to it. So let us find those. So we set the determinant of A minus lambda I equal to 0 and solve for lambda. So the determinant is 1 minus lambda 5, 2, 4 minus lambda. So that's a simple one, minus 10. Now you take it, you multiply things out by each other, you get lambda squared minus 5 lambda minus 6 equal to 0. Now to solve is basically to factor. So we factor, I get 1, 6, plus 1, and minus 6, lambda squared. So we have 2 eigenvalues, minus 1 and lambda equal to 6. Okay, now for each eigenvalue, we have to find the eigenvectors, and I need 2 linearly independent one to be able to diagonalize. So we start with the first one. So step 2, we need to find a basis for E minus 1. It means the eigenspace that correspond to lambda equal minus 1. So now I'm after eigenvectors. I need linearly independent one. I don't need all of them. I need 2 linearly independent ones. Okay, so we do that. Lambda equal minus 1. So here we have to solve. And because lambda is negative, we have to be careful. A minus x equal to 0. which is basically a plus I equal to 0. So be very careful when lambda is negative. Look, now we just plug in here. We take the homogeneous system and we plug it. We get my A is 1. I'm going to add 1. That's going to give me a 2. And that's it, 2. 5. And my 4, I'm going to add a 1 to it. Would give me a 5. And that's 0, 0. Remember very carefully, if you do not get a free variable, what you're doing is wrong, because the determinant, the way we found a lambda is by making the determinant equal to 0. So the determinant of this matrix have to be 0. We have to have a non-zero solution. So this is obviously 1, 1, 0, 0. You don't need a lot of steps. And I need to write this in vector form. So my x2 is 3. And my x1 is minus x2. So every eigenvectors means every vector that has the property ax equal minus x will be of the form t times minus 1 and 1. So a basis for e minus 1 is the vector minus 1, 1. So it means that there are a lot of eigenvectors that correspond to lambda equal minus 1. Every scalar multiple of that is an eigenvectors. But to be diagonalizable, I need 2 linearly independent. And here I only have 1. So I need somehow to get another one, another eigenvectors to be able to proceed. So, but I have another eigenvalue. I go after it. So step 3, we find a basis that correspond to the other eigenvalue, which is lambda equal to 6, because I need 2 linearly independent. I only have 1 so far. Basis for E6. We do the same thing. So we're going to solve a minus 6i equal to 0. And we go after it. Very well. So let me go after it. So a minus 6 I 0 will give me the following. 1 plus minus 6, so I will get a minus 5. So this is my matrix A. I'm taking minus 5 along the diagonal. I have a 2, I have a 5, and I have to take also 6 along this from this diagonal. So I'm going to get a 2 here. I get a 5, and then I will have 4 minus 6, which is going to give me a minus 2, 0, 0. Again, I have this matrix. I have to reduce it. And of course, it's a very simple one. Minus 5, 2. I'm adding the 2 row, 0, 0. Okay. Now I solve. And then what do I get? T times. Okay. So when I'm going to solve here, when I'm going to solve, okay, I'm going to get x2 free. And the first equation will read minus 5x1 plus 2x2. So it means it's going to give me x1 is 2/5 x2. So x could be written as t times 2, 5, and 1. Okay. So a basis for E6, is a basis for E6. It means is. Now you have your choice of basis. You can pick 2/5 one as a basis, or because fractions are not fun to work with, you can take for basis 2, 5. It's just easier to work with. Or 2/5 one, you're free to take every one of them. All right, so now what do we have so far? So far we have the following. We had 2 eigenvalues, lambda equal minus 1, lambda equal to 6. For lambda equal minus 1, all the eigenvectors are scalar multiple of minus 1, 1. That was the basis. That was a basis. For lambda equal to 6, then my basis vector was 2, 5. So that's my eigenvector, and it is my basis. That's what I have so far. Now I have a lot of other eigenvectors. Every scalar multiple of that is an eigenvector that corresponds to lambda, and every scalar multiple of that. Now for a matrix to be diagonalizable, I need 2 linearly independent eigenvectors. And the question is, do I have 2 linearly independent eigenvectors? I need 2 of them. If I notice here, let us note that the following vectors, minus 1, 1, those are eigenvectors. And 2, 5, since they are 2 vectors, we can just by looking at them know that they are linearly independent, are 2 linearly independent eigenvectors for A. So now I have 2 linearly independent eigenvectors of A. And now the criteria for diagonalization tells me the following. A matrix is diagonalizable if it's in n by n, is diagonalizable if it has n linearly independent eigenvectors. Now this is a 2 by 2. Since we were able to find 2 linearly independent eigenvectors, so note that so my matrix A can be factored out or diagonalizable. Means I can really write it as the product of simpler matrices. So it means that A could be written as a P times a D times P inverse. Now what's P? What's D? And what's P inverse? What's P? What's D? P is the matrix whose columns are the eigenvectors. So the columns are the 2 linearly independent eigenvectors. That's the first one. And that's the second one. Now what's D? D is the matrix, it's a diagonal matrix. It's diagonal. And along the diagonal, the term along the diagonal are the eigenvalues that correspond to the eigenvectors. So it means the following. If this is minus 1, 1, what should go here is the eigenvalue that correspond to minus 1, 1. That's the part we should be careful with. So if it's minus 1, 1, now remember minus 1, 1 came from the eigenvalue. That's the eigenvalue that correspond to it. So that's going to be minus 1, 0. And 3, 5, we put the eigenvalue that correspond to it, which is equal to 6. Okay. Isn't 2, 5? Oh yeah, thank you. 2, 5. What's important is, we have to be careful is the following. If I picked minus 1, 1 here, the eigenvalue that goes in the first column should be the one that corresponds to minus 1, 1. I pick 2, 5 here, the eigenvalue that correspond, the term of the diagonal that correspond, that should be here is the eigenvalue that correspond to 2, 5. So the only thing we have to be careful with is we cannot mix match eigenvalues. So now A could be written A. So A is equal to P times D times P inverse. P times D times P inverse. Now I will compute P inverse because it's easy. My P here is that, so I can break it up totally. My D is this one. And P inverse is just the inverse of that. And if we remember how we find the inverse for a 2 by 2 matrix, it's not really hard. For a 2 by 2 matrix is 1 over the determinant times the following. What's on the diagonal? We get switch. And the term of the diagonal, so that's P inverse, will be multiplied by a negative 2. And this should be the determinant, which is minus 5 minus 2, which is minus 7. So P inverse is going to be minus 5 over 7, 1 over 7, 2 over 7, and 1 over 7. Okay, and that's really my decomposition of the matrix A. Now, once I decompose it, one thing we can do, we can compute its power. Suppose I tell you compute A. So basically now, if you take the three matrices, if you want to check your work, take the three matrices and multiply them by each other, physically multiply them, you're going to get A. If you get anything but A, it means this decomposition is not really, it's wrong. So multiply those, you should get A. That's really how you check your work. Now, if I tell you compute A to any power, 10, 15, I don't really care which power. And then we can do that in a simpler way. It's going to be times. So P inverse remain, won't be touched, to 7. And this, every term will be raised to the power 10. 0, 0, 6 to the power 10. Okay, so multiplying the matrix is one of the simple applications, is actually becoming fairly simple. Okay, so that's an example of a matrix which can diagonalize. Of course, we cannot diagonalize every matrix, and now we're going to have other examples. But before I do my other example, I want to make one thing very clear about those before I proceed. Suppose a student for P picked for eigen the first column is 2, 5, and the second minus 1, 1. Suppose a student did that. Then for this student, the diagonal would be, if this is 2, 5, 2, 5 is coming from the eigenvalue 6, then this should be 6, 0, and that should be 0, minus 1. That's what will happen. So if you switch the order here, you have to switch it here. That's what you should be careful with. It doesn't matter which one you pick, that's irrelevant. They all give us the matrix A. All right, so now we're going to do 2 more examples to basically cover all our bases. So example number 2, I'm going to take A to be the following matrix. Uh, 1, 0, 0. I'm going to try to take easy matrices, 0, 2, 0, and 0, 1, 2. And the question is diagonalize if possible. If not, you have to justify why not, if possible. Okay, this is a 3 by 3 matrix. This can be diagonalized. It means can be written as product of simpler matrices, P times D times P inverse, if it has 3 linearly independent eigenvectors, which is what I said you need eigenvectors that can in a way form a basis for R3. That's really the idea. So we need 3 linearly independent. That's the condition under which we can diagonalize. So the only way, by looking at it, I have no idea whether I can do it or not. I just have to go after those eigenvectors. If I can create those 3, I'm fine. If I can't, it means we cannot diagonalize it. So we have to go through the process, the whole process. So the step number 1, we have to find the eigenvalues. And then we take the determinant of A minus lambda I equal to 0 and solve for lambda. Now, last time if you guys remember, this is really a very simple matrix. It's 1 minus lambda, 0, 0, 0, 2 minus lambda, 0, 0, 1, 2 minus lambda. Remember, I mentioned last time that this is actually what we call a triangular matrix. Because a matrix where everything below the diagonal is 0. So if you have a diagonal matrix, then the determinant is the product of the term along the diagonal. So this is 1 minus lambda times 2 minus lambda squared. But it has to be triangular. And this is triangular because everything here is 0. Or you can compute the determinant. It doesn't really matter. So this is equal to 0. And then we solve. Lambda equal to 1. That's an eigenvalue. And another one is lambda equal to 2. And this one we said that is of algebraic multiplicity 2. Okay? That's what we call that. All right, now we have to go after the eigenvectors. And to go after the eigenvectors, I have for each one of them, I need to find the eigenvectors. I have 2 of them. So let us find them. So for E1, so we're going to find, so step 2, we're going to find the basis for E1. Okay. And then I need to solve A minus. So here lambda is 1, so it's not negative. So I need to solve that. Okay, so I'm going to plug in 1 here and proceed. I will have 1 minus 1, this is 0. And then here I'll have 0, 1, 1. And here I'll have 0, 0, 1. Okay, don't let lots of zeros confuse you. Remember, we have to go to the echelon form, regardless what the matrix is. To go to the echelon form here, all the row of 0 has to go down. Okay, and then I have to make sure that I have my triangular form. So I'm going to put row 2 on the top, and I will put row 3 right here. And by doing so, I just exchanged rows basically, but I made sure by exchanging my rows that I have my matrix is in echelon form. And now I need to solve. I think I can solve right there. I have a leading, this is a leading, and this is a leading. My vectors are in R3 because we're looking for the vector that we multiply by x, by a, to give me scalar multiple of a. So I have 3 unknowns, x1, x2, and x3. In this problem, what's interesting is that we don't always run into this. x1 is free, because there is no leading in the first column. And this is x3 is equal to 0 by reading this row. Now the second row read x1, x2 plus x3 equal to 0. It means x2 equal to 0. And this is my variable t. So my eigenvectors, every eigenvectors is going to be written as t 0, 0, or the scalar t times 1, 0, 0. And so a basis for E1 is the vector 1, 0, 0. So I have one eigenvector so far. I have a lot of eigenvectors, but all of them are scalar multiple of 1, 0, 0. To be able to diagonalize, I need 2 more, and I want all 3 of them to be linearly independent. But I have another eigenvector value to deal with. So we're going to do that, and we're going to proceed. Okay, lambda equal to 2. And we're going to find eigenvalues for that. So we're going to find a basis for E2. All right, so to find a basis for E2, I have to do the following. I need to solve A minus 2i equal to 0. And let's see what I get. Okay, this is my A. I have to take 2 away. 1 minus 2 minus 1, 0, 0. And I have 0. I have to take 2 away from this and the 1, 0, 0, 1. Here I have to take 2 away, 0, 0, 2 minus 2 is 0. Now I have to solve that. Okay, this is leading. This is leading. I am in echelon form. Then x2 is going to be my free variable. So now I will get the following. x2 is free. x1 is 0. And x3 is 0. And this is, I'm going to set this equal to t. So every eigenvectors will have the form t times 0, 1, 0. So a basis for E2. E2 is all the eigenvectors. So it means that E2 now is nothing more than the span of this one vectors, because it are all possible eigenvectors that correspond to lambda equal to 2. Each one of them is a scalar multiple of that. So I have 0, 1, 0. That's a basis for it. So now what's the picture for now? The picture is this. We had two eigenvalues, lambda equal 2, and the other one we had was lambda equal to 1. For lambda equal to 1, the basis vector was 1, 0, 0. Means every eigenvector is a scalar multiple of that. For lambda equal to 2, we found that every eigenvector is a scalar multiple of that. For my matrix to be diagonalizable, I need 3 linearly independent eigenvectors. But can I get 3 linearly independent in this picture? Every eigenvector is either a scalar multiple of that or a scalar multiple of that. So I actually don't have a third one to work with. So this matrix A doesn't have 3 linearly independent. It has only those two. Everything else is scalar multiple. A doesn't have 3 linearly independent eigenvectors. So A is not diagonalizable. So A is one of those matrices that is not diagonalizable. Means there is no way I can actually factor it out this way. We cannot factor it out this way. Now, if you guys ever study more advanced classes in linear algebra, there is another way we can factor the matrix A, but it's to make it easier to work with, but it's definitely not the one we are learning in this course. But there are other factorization of this matrix. Right? So I am not finalized, but I will give one last example, but I try to be a little bit more compact for a 3 by 3. Another example for a 3 by 3. So this is example of matrix that I cannot really break it up. So my last example for 3 by 3 is the following. Again, my goal is to take simpler example. So I'm going to take the matrix A to be -1, 3, 1, 0, 0, 0, and 1 minus 3 minus 1. And my question is, can I break A apart? Can I diagonalize A? And if so, do it. Okay. Again, looking at it, I have no idea whether I can do that. So always I have to go after. So we're going to find eigenvalues. Okay. Now finding eigenvalues is actually a very hard problem in general. Because if my matrix, even if my matrix is 3 by 3, the determinant of A minus lambda I usually is a cubic function. It means it's a function in lambda 3. And solving a cubic equation, as probably you guys know by now, is actually not really easy. So finding eigenvalues is not a trivial problem, and there is tremendous amount of algorithm written to find them. I mean, Google has one of the most famous algorithm to find the eigenvalue. It's not easy. If a matrix is 4 by 4, the eigenvalues, the determinant is going to be a polynomial of degree 4. And remember, solving the determinant means I have to solve a polynomial of degree 4, which is tremendously hard. And as I said, there are a lot of algorithms to approximate the eigenvalues. So it's not really easy, except those I give you in class, those are easy. But in general, it's not a very trivial problem to do that. So, but we're taking easy stuff. So this is 0. I have to take a lambda away. So it's give me a minus lambda. I have to take a lambda away, which give me minus lambda. Okay. And as I said, I give you problems which are simple. So this, you go after the second column to compute the determinant of that. That's the easiest one. So you will get plus, minus, plus, and you get this one. So this will go 1 minus 1 minus lambda. And okay, so you will get minus lambda times, this time that is basically like 1 plus lambda square minus 1. And you do all the math you need to do. And you get lambda squared times lambda plus 2. Okay, you guys do the math. And we're going to set this equal to 0. I'm going to have two eigenvalue, lambda equals 0 and lambda equal minus 2. So again, I have an issue of two eigenvalues like I had in the previous one. And this is algebraic multiplicity 2. Because lambda, when we factored, lambda square occurred twice. And this is algebraic multiplicity 1. Now, the question is, do I have enough eigenvectors? Again, I don't know the answer till I go after them. So I'm going to find them. So first, we're going to find a basis for E0. Okay, and then I go basis for lambda equal minus 2. All right, so base for E0, it means I need to solve the following problem. I need to solve A minus 0ix equal to 0, because that's my lambda. It means basically I need to solve ax equal to 0 because lambda is 0 in this case. So basically I'm boiling down to solve the system ax equal to 0. So, okay, we're going to solve it. It's minus 1, 0, 1, and that's a 0, 0, 0, 3, 0, minus 3, 1, 0, minus 1. Okay, let us do that. So minus 1, 0, 1. I multiply by 3. Minus 3 plus 3 is 0, 0, 0. Minus 1 plus 1 is 0. That's a 0, and that's a 0. That's what I get. And now let us analyze what we have. I have one leading. It means I have two free variables. So x2, x3 are free. So if you think a bit about it, those three equations are the same in a way. So I'm really having one equation. So let's write this down. It means I have x2 free, x3 free. And x1, this read minus x1 plus, so the first row read minus x1 plus x3 equal to 0. It means x1 equal to x3. So they have two free variables. So I'm going to set this to be an S, and this is to be a T. And now I have always to write the solution in vector form. So now we write the solution in vector form. So in vector form, we get in vector form, we get x equal S times, because I have two free variable, plus T times. The first one, because this is x3, so this is a T. So it's going to give me a 0, a 1, and a 0. Now for the second one, I'm going to have a 1, 0, and a 1. Okay, so it means that the eigenspace that corresponds to lambda equal to 0 is all the possible eigenvectors. It means all the linear combination of those two vectors. So it's the span of those two vectors. It's actually the span. Now, those two vectors, of course, if you look at them, they are linearly independent. It means the basis. For E0, it means all the vectors. So I'm basically computing the null space. It means all the vectors that satisfies Ax equal to 0 because lambda is 0. So I'm really after the null space here. So the bases are the vector 0, 1, 0, and 1, 0, 1. And they are linearly independent, as you can see them. So the picture now is, I have two eigenvalue. For lambda equal to 0, I found two linearly independent eigenvectors. Diagonalization required 3 of them, but I still have another one I have to go after and see if I can pick up a third one. So now for lambda equal to 1, part 2 is we need to find a basis for the other eigenvalue that's left for us. The other eigenvalue is lambda equal to 2. Okay, and then let us do that. So we have to solve a minus 2ix equal to 0. Again, we solve that. We solve it verbatim. A and we proceed. We do exactly what we've been doing over and over. So this is my matrix A. I have to take 2 away. So I will have -3. And then I'm going to have a 0 and 0 and 1. And I keep going. I will have a 3. I will have a -2, -3. And then I will have a 1. I'll have a 0. And then I have to take 1 away, which is going to give me -3. And then I need to actually solve this. Okay, so if I solve it, I'm going to get, because we've done this several times, equal to a certain scalar times -1, 3, and 1. Okay, you go to the echelon form and you proceed. So a basis for E2 is actually the vector -1, 3, 1. So now let us see what we have. So we sum up. So we have two eigenvectors, eigenvalues, 0 and 2. For 0, I have two linearly independent. I have 1, 0, 1, 0, and 1, 0, 1. Everything else is a combination of that. For lambda equal to 2, I have those vectors. Everything else is a combination, a scalar multiple of this. So the question now is, do I have 3 linearly independent eigenvectors? Okay. So now we need to check. We check that those 3 vectors are linearly independent. It's not very hard. So now we can check that 0, 1, 0, 1, 0, 1. They're all eigenvectors. Those are linearly independent. Okay, it's actually easy to check that. So now the criteria is satisfied. So they are linearly independent. It means my matrix A has a basis of eigenvectors. It means A had 3 linearly independent eigenvectors. So A is absolutely diagonalizable. So even though lambda equal to 0 was repeated, but I was still able to find 2 eigenvectors are independent that correspond to lambda equal to 0. And I picked another one from lambda equal to 2. It's easy to check that they are linearly independent. It means it is diagonalizable. So now let us diagonalize it clearly. So I can write A as P times G times P inverse. I can actually break it. And let us see what the P is. The P is the matrix whose columns are those eigenvalues. So, sorry, the eigenvectors, which are 0, 1, 0, 1, 0, 1, and -1, 3, 1. Those are the linearly independent. And because they are linearly independent, because it's easy to check, as I told you, this matrix will be invertible. Otherwise, we cannot really find its inverse. What's the D? The D is the following. 0, 1, 0 is the eigenvector that corresponds to lambda equal to 0. So D is going to be 0, 1, sorry. That's correspond to that. That's the eigenvector. Right here, the eigenvector that corresponds to that is also 0. So it's going to be 0, 0, 0. The eigenvector that corresponds to this last one was 2, 0, 0, 2. That's what my diagonal. Now, it has lots of 0 because that's the value of the eigenvector. So finally, my matrix A, I can write it as my P times my D times my P inverse. Okay. I'm not going to compute P inverse. We've done this a million times, but I'm going to emphasize the new thing, which is this diagonal. So I can totally break up my matrix into simpler matrices, especially the diagonal piece. It's such a single matrix that helped me to work with my matrix A very well. Okay. All right. The last thing I would like to talk about, mention in the diagonalization, is a theorem that it is useful. I will read it carefully and I will actually explain it. So the theorem tells me the following. When I found those eigenvalues here, eigenvectors, and then I said we have to check that they are linearly independent. Now, there is a theorem that tells us that guarantee for us that the eigenvectors that correspond to distinct eigenvalues are always linearly independent. So let me read it and then I will explain it in work. Tell me the following. Suppose we have a n by n matrix. We have a matrix. And we have a bunch of eigenvectors. So v1, v2 through vk. And those eigenvectors correspond to distinct eigenvalues. It means eigenvalues are not the same. So the eigenvalue correspond to v1 is different than the one to v2, different than the one from v3. Then automatically, those eigenvectors will be linearly independent. So if I have eigenvectors v1 correspond to lambda equal to 1, v2 correspond to lambda equal to 2, v3 correspond to lambda equal to 3. So there is a theorem that tells me that immediately v1, v2, v3 will be linearly independent. Now the proof was a little bit beyond our class, that's why I dropped it. I cannot prove it for you. So this theorem would lead us to a case where diagonalization is automatic in the following sense. The matrix A has n distinct, different eigenvalue, then it's immediately diagonalizable. Let me explain that in words. It means if A is 2 by 2, I have 2 different eigenvalues, immediately we can diagonalize it. It doesn't tell you how, we have to do the work, but we know it is. If A is 3 by 3, it has 3 distinct, then we can diagonalize it. But if A is 3 by 3 and it has 2 distinct eigenvalue, then we can go either way. And the 2 examples I gave you, in one case, we were able to do it, in other case, we were not able to do it. So for example, if I take the following matrix here, this matrix, 2, 0, 0, minus 3, 5, 0, this matrix, the eigenvalues means when I'm going to compute this, the eigenvalues are going to be 2, 5, and minus 1. Because when I take minus lambda, minus lambda, minus lambda, and I compute the determinant, I'm going to take the product along the diagonal. So this one will give me 2, 5, minus 1. So this matrix automatically will be diagonalizable because it has 3 distinct eigenvalues. But if you want to diagonalize it, we have to go through the whole process. It means we have to find the eigenvectors that correspond to 5 minus 1, and then we can diagonalize after. Okay. All right, so I stop at here today, and your quiz on, you guys have a quiz on Wednesday, and we'll cover all the homework I assigned for today. As you guys know, your exam, I think I put that on Brightspace, and I put the review on Brightspace. Your exam is next Monday. Now the time given on the schedule, it means that's Purdue schedule, not mine. The exams start at 2:45. my memory to 4:45. So that's the scheduled time for our exam. And I'll give you, as usual, I give you half an hour extra from here. So you guys do whatever you do to upload or download, and half an hour extra in here. Okay, so which will give you 3 hours for the exam. Okay, so the final will be comprehensive, and the best way for you to review for the final is actually you have a lot. So I will not give you extra review. You have 2 old exams, you have your 2 exams, and the new material, which is basically eigenvectors and eigenvalues that I've been quizzing you over. And that's it. You guys have any questions? Any questions? Okay, so as I said, your quiz on Wednesday will cover the same stuff: eigenvectors, eigenvalues, and diagonalization. Good luck. Can you bring up the last sheet if I remember which one? This one, Chris? Okay, time is up. You guys can go. I will keep this up for Chris to copy it. Yep. Are you guys done? Okay, I will end the meeting. Bye-bye, guys.